There are two types of waves. There are longitudinal waves, and there are transverse waves. Let's talk about the difference. In a longitudinal wave, you'll have a particle, and it'll oscillate to the right and to the left in a periodic or repeating pattern. In addition to the fact that the particle is oscillating, in this case horizontally, the energy is also being transferred in one of those directions horizontally as well. So because the particle is moving left and right, and the energy is moving left or right, we would say that these two directions are parallel, which means that the particle is moving or oscillating parallel to the direction of energy transfer. A transverse wave, however, is different because you'll have a particle that'll oscillate up and down, or vertical in this case, yet the energy is still being transferred in one of the horizontal directions. So because there is a right angle between that particle oscillation direction and the energy transfer direction, we would say that these two directions are perpendicular. So that's the main difference between longitudinal and transverse. Longitudinal waves are how a lot of waves work in real life in terms of pressure waves. So shock waves for earthquakes or sound waves through the air, they're going to be areas where particles are closer together or farther apart. But these kind of waves are kind of tricky to draw. We'll see how they're animated in a second. So we oftentimes draw waves as transverse waves, even though in real life they're longitudinal. And there are some analogs between longitudinal and transverse waves that allow us to draw most waves as transverse waves. Here are the parts of a wave. The peak of a wave, or the highest point, that's called the crest on transverse waves. And we see here that we have 1, 2, 3 crests on this transverse wave. The analog in the longitudinal wave is where the particles are closest together. The opposite of a crest, so the bottom of the wave, is called the trough. And here we have 2 troughs on the transverse wave. The analog in a longitudinal wave is where the particles are spread out the most, or the farthest apart. The distance between any 2 crests that are adjacent, or any 2 adjacent troughs, is called the wavelength. So we can draw in the wavelength here. The wavelength would be between these 2 crests. There is a symbol that we use to denote wavelength in chemistry and physics, and that is the upside down looking Y. It's a Greek symbol that means lambda. Now, wavelength can be larger or smaller, and that affects things like frequency and other things we'll talk about. So these are the main things that you need to know for a wave, but we're missing something important that is actually easier to see on a transverse wave. There are 2 things that people often get mixed up. One of them is wave height, and the other is amplitude. Wave height is the difference between the crest and the trough. So this right here represents wave height. Wave height is different from amplitude. Amplitude is the distance between the resting point, or the equilibrium of the wave, and the crest of the wave. So this right here is called the amplitude, which we abbreviate as just A. So those are the main things you have to know for the difference between longitudinal and transverse waves, and the parts of a wave, which are much easier to draw and understand for transverse waves. Waves move. So we have a wave moving to the left and a wave moving to the right. Notice how they have 2 different heights. One is 2 and one is 3. So when they're perfectly superimposed or on top of each other, they combine to create a wave that has a height of 5. Let's find that location. So we have our 2 waves, a 2 and a 3. When they are perfectly superimposed, which is going to be around here, notice how they have a new wave height of 5, 2 plus 3. This is called constructive interference. Constructive interference occurs when a wave and another wave combine to create a larger wave. Their heights actually add up. Now we have 2 waves with 2 opposite amplitudes, a positive 3 and a negative 3 in terms of their height. As they approach each other, they're going to become superimposed and totally cancel themselves out at that moment. This is called destructive interference. Let's find the time. So when the waves are about to pass each other, right when they're superimposed, notice how the positive 3 and the negative 3 of the other one cancel out. This is destructive interference, which is the opposite of constructive interference. Here we have 2 waves moving in opposite directions. They have the same wavelength and they have the same amplitude. What's happening here is that they are doing both constructive interference and destructive interference. So when their crests are aligned, they have a combined larger wave, which is constructive interference. But when a crest of one wave is on top of a trough of another wave, then you have destructive interference. So what happens when the wavelength or the amplitude are different? That's when you get some interesting wave patterns due to the constructive and destructive interference. So if we change the wavelength of the blue wave and we keep the red wavelength the same, you get this interesting combination and these beautiful patterns. If we were to change the amplitude of the red wave, for example, it changes the pattern even more. So go ahead and play around with this. It's on ophysics.com and it's free.